Hello my dear friends, I welcome you all for this lecture. So today we will discuss about the chapter number 6 electromagnetic induction. Okay, so the previous three videos were discussed about the introduction part of the electromagnetic induction. After that we have studied the Faraday's three experiments of electromagnetic induction, and after that the Faraday's laws of electromagnetic induction and Lentz's law. So here today in this video we will discuss about the some expression that is based on the two laws, okay, that is Faraday's laws of electromagnetic induction and Lentz's law. Okay, so this is the expression for induced EMF that is based on the both laws. Which both laws? The first law, that is the electromagnetic induction laws, okay, that is the Faraday's laws of electromagnetic induction, and the another one law is Lentz's law. According to the Faraday's laws, okay, Faraday's law of electromagnetic induction, the magnitude of the EMF is induced in the circuit is equal to what? Rate of change of magnetic flux linked with the coil. And the Lentz's law says the polarity of the induced EMF is such that it tends to opposes the current which is the change in the magnetic flux that produced in it. Okay, so that two laws were studied in the electromagnetic induction part 3. Okay, if you don't remember, please go through the electromagnetic induction part 3 video, and after that you see this expression. Okay, so today we'll discuss about the expression of induced EMF that is based on the both laws, Faraday's law and Lentz's law. So according to the law, E is equal to minus d phi by dt. Okay, so that is EMF is equal to the rate of change of magnetic flux. So d phi we may write as a phi 2 minus phi 1 divided by t. Okay, E is equal to minus phi 2 minus phi 1 divided by t, where n is the, suppose, the number of turns of the coil. Suppose for the one coil, okay, the number of one turn of the coil is equal to minus d phi 2 minus phi 1 by t. For n number of turns of the coil, we will take E is equal to minus n d phi by dt. Okay, for one turn of coil, E is equal to minus d phi by dt. For n number of turns of the coil, that is E is equal to minus n d phi by dt. Or I may write this as a E is equal to minus n phi 2 minus phi 1 by t. Then the expression for induced current, I may write as a I is equal to minus R into d phi by R into dt. Okay, so it is a expression for current. Okay, so here the expression for induced current is I is equal to minus d phi by R into dt, and the expression for charge is dq by dt is equal to minus d phi by R into dt. So suppose here in this the dt you should cancel. So dq is equal to, I may write, minus d phi by R. So dq is equal to what? Minus d phi by R. This is the expression for charge. And expression for induced current is I is equal to minus d phi by R into dt. And the expression for charge is dq is equal to minus d phi by R. Where note, the induced EMF does not depend on the resistance. Okay, so it is not depends on the R of the circuit, where as the induced current and induced charge depends on the resistance. Okay, so only induced current and induced charges are present, but the EMF is not present on the resistance. So after that, we will discuss about the methods of producing induced EMF. Okay, the methods of producing induced EMF. The first one, that is by changing magnetic field B. Okay, the first method, by changing magnetic field B. The magnetic flux phi can be changed by changing the magnetic field B, and hence EMF can be induced in the circuit as done in Faraday's experiments. Okay, the magnetic flux phi can be changed by changing magnetic field B, and hence EMF induced in the circuit. Okay, so if the coil or the magnet, between that two, if relative motion will be there, then only flux is changes. If the magnetic flux is changes in the circuit, it means the magnetic field B is also changes. It means EMF can be induced in the circuit. So that we are studied in the Faraday's experiments also. By changing magnetic field B, we can produce the induced EMF. Okay, this is the first method. Okay, by changing magnetic field B, we can produce the induced EMF. This is the first method. And after that, by changing the area of the coil A available in magnetic field. So how? By changing the area of the coil and that is available in magnetic field, how we can produce it in it. Okay, that we'll see. Suppose the magnetic flux phi can be changed by the changing area loop A, which is acted upon by the magnetic field B, and hence the EMF can be induced in the circuit. So suppose here these all are the points. Okay, these are points. So here in every point of this surface is having the same magnetic field. Okay, here B is the magnetic field. So this is the area is having the magnetic field. Okay, in this area the same magnetic field is present, that is B, capital B. Okay, so the capital B is the same magnetic field is present, and every point of this area is having same magnetic field. Then after that, suppose the PQRS, or we will take is, suppose the PQRS, suppose PQRS, okay, this is the area, is slided into uniform and perpendicular magnetic field. Okay, so it is moving with a velocity v. Okay, v, it is sliding in this direction. Okay, in this direction. Then the change or increase in area of the coil under the influence of the field is dA. Okay, so this is a dA is a, this is the area of the coil. Okay, that is increased in this magnetic field, uniform magnetic field, in time dt. This causes the increase in magnetic flux d phi. Okay, so it increases the magnetic flux d phi. Or the induced EMF is due to the motion of the loop, and so it is called uniform or the motional EMF. So what is meant by this motional EMF? Motional EMF is what? It is the EMF induced in the conductor moving in the magnetic field. Okay, the motional EMF is what? Motional EMF is the EMF induced in the conductor moving in the magnetic field. Okay, and it is the EMF due to the motion of the loop, and so it is called the motional EMF. Okay, in so because of the motion of the that moving conductor, the whatever the EMF produces, that is known as motional EMF. If the loop is pulled out the magnetic field, so that is E is equal to BLV. How that E is equal to BLV? We'll see here. Suppose the d phi is equal to B dot dA. Okay. So why this d phi is equal to B dot dA? So the d phi is equal to, that is, the B is a magnetic field and dA is what? The area changes under the magnetic field. Okay, area increases under the magnetic field in rate of dt. So suppose here we know that the dA we can take as a L into V into dt, because this length is L and this is V dt. So area of this square is what? Length into breadth. Length is L and breadth is V dot dt. So that is d phi is equal to B dA is a area as a L, this L into V dot dt. So this, but we know that the EMF is equal to minus d phi by dt. So here d phi is equal to B dot L dot V dot dt. That is BLV into dt. Dt take this side. So that is d phi by dt is equal to BLV. Therefore, E is equal to minus BLV. So that is E is equal to BLV. Okay, that is the loop pulled out the magnetic field. Then the EMF is equal to BLV. And the direction of induced current is anti-clockwise in the loop. Therefore, the P, that is P dash, S dash, R dash, Q dash, okay, and P dash. By the Fleming's right hand rule, it applies the Lenge's law. Okay, using Fleming's right hand rule, it applies the Lenge's law. Or we'll deduce the expression for the EMF induced across the ends of the conducting rod moving in a perpendicular magnetic field. Okay, so this is the very important expression. So that is the expression for EMF induced across the ends of the conducting rod moving in perpendicular magnetic field. So consider here, this is the magnetic field. Okay, uniform magnetic field. Every point of this field is having magnetic field as a B. Okay, B is a magnetic field. Uniform magnetic field area is present. After that, the suppose here the P S dash P dash is the rectangular conducting loop placed in uniform magnetic field. Okay, so P S dash P dash, that is P S S dash P dash is a uniform rectangular conducting loop, okay, that is placed in uniform magnetic field. Suppose the PS is a one part of this rectangle and it is freely moving with a velocity v, okay, it is moving with a velocity v in this direction, okay, inward direction. Suppose it is moving and B is a magnetic field that is normal to the plane of the paper and directed inward, okay. So B is the magnetic field that is normal to the, here the magnetic field and the whatever the plane is present, okay, that area is present, both are normal to each other, and the B is a magnetic field that is normal to the plane and it is directed inward direction. Then suppose I is the current, okay, of length of this conductor, okay. So this is a area you consider as a one conductor and the length of the conductor PS, okay. So this length of the conductor PS, okay, this much length is present of that conductor, that is PS. Suppose V is a uniform velocity with which conductor PS is having, okay, uniform velocity V with which it is moving in magnetic field direction, inward direction, and X is the distance traveled by the conductor. Suppose X is the distance, this is the X, okay, that is traveled by the conductor. After that, when the conductor PS is moving towards the left side, okay, so this conductor PS is moving inward direction, left side direction. That time here all the free charges of the conductor, okay, that PS experience a force because of the free charges of the conductor. PS experience a force and this produces the current through the loop, okay. This produces current through the loop PS S dash P dash, that is, okay. So the current through the loop is present in that PS S dash P dash as shown in our figure, okay. So that is the PS S dash P dash, in this loop the current is present, okay. And after that, if the current is present, then the magnetic flux enclosed by the loop, and the flux is equal to what? I will write B into area of the loop, okay. So B is a magnetic field, B into A, okay. B is a magnetic field, B, and area is what? That is this length and breadth, okay. So area of this loop, so that is having some length and breadth, okay. So that is area of the loop as a length, okay. So suppose L is the length, this L is the length of this PS, and breadth is X. S dash is having breadth as X. So L into X is the area of this loop, okay. So that is the B into L into X, okay. Area is length into breadth, L into X in this above figure. Then from the Faraday's law of magnitude of the induced EMF, that is E is equal to d phi by dt. According to Faraday's law, the magnitude of EMF is a rate of change of magnetic flux. E is equal to d phi by dt. And from the equation 1 and 2, E is equal to d by dt of BLX. Okay, that is d by dt of BLX, because phi value is what? Phi is equal to PLV from the equation number 1. So the E is equal to B into L into dx by dt. So, but dx by dt is equal to V, because V is equal to velocity is equal to rate of change of displacement. So V is equal to dx by dt. So because of that, E is equal to BLV. So this is the expression for EMF induced across the ends of a conducting rod moving in a perpendicular magnetic field. Okay. Thank you.